Perfect. Let's start from the ground up and make Ohm's law sound as clear and natural as if you were hearing it in a classroom without using any digits, only full words. The heart of electricity, Ohm's law. Ohm's law is one of the simplest and most powerful ideas in all of electrical science. It tells us how voltage, current, and resistance are related to one another in any electrical conductor. In words, it says, open quote, "The current flowing through a conductor is directly proportional to the voltage applied across it and inversely proportional to its resistance." Close quote. That means if you increase the voltage, the current increases, and if you increase the resistance, the current decreases. The three quantities. Let's look at the three ingredients that appear in Ohm's law. 1. Voltage, measured in volts, is the electrical pressure that pushes charges through a circuit. You can imagine it like the height difference in a water system. The higher the pressure, the more strongly the charges want to move. 2. Current, measured in amperes, is the flow of electric charge, the rate at which electrons are moving through the wire. It's similar to how much water passes through a pipe per second. 3. Resistance, measured in ohms, is how much the material resists the flow of that current. A high resistance acts like a narrow pipe. A low resistance acts like a wide pipe. The relationship in algebraic form, we usually write Ohm's law as open quote, V equals I times R, close quote, where V is voltage, I is current, and R is resistance. But in plain language, that means, open quote, the voltage across a component equals the current through it multiplied by its resistance, close quote. So if you know any two of these quantities, you can always find the third one. For example, to find the current, divide the voltage by the resistance. To find the resistance, divide the voltage by the current. To find the voltage, multiply current by resistance. What it really means physically, imagine you have a long, thin wire. If you push a small voltage across it, only a small current flows. Double that voltage and the current doubles as well, provided the wire stays the same temperature and material. That linear relationship between voltage and current is what defines an ohmic conductor, one that obeys Ohm's law. Many metals behave this way over a wide range of conditions. However, not all devices are perfectly ohmic. For instance, semiconductors, diodes, and transistors have nonlinear current-voltage relationships. But Ohm's law remains the basic reference that describes how electrical quantities connect. Why it's so important, Ohm's law is the foundation for nearly all circuit analysis. Every time you design or troubleshoot a circuit, whether it's a simple resistor or a complex power converter, you're using Ohm's law at its core. It helps you determine how much current will flow for a given voltage, how much resistance or load you need to set that current, how much power will be converted into heat or work. Power and energy connection. Once you know voltage and current, you can also calculate electrical power. Power equals voltage multiplied by current. Combine that with Ohm's law, and you can express power in several equivalent ways. Power equals current squared times resistance. Power equals voltage squared divided by resistance. These relationships are what engineers use to calculate heating, efficiency, and component ratings. In summary, Ohm's law is the rule that connects the three essential electrical quantities, voltage, current, and resistance, into one elegant relationship. It tells us that current grows with voltage and shrinks with resistance, and that voltage is the measure of how strongly the circuit pushes that current through its resistive path. It's simple, universal, and it sits at the foundation of everything from tiny electronic circuits to high-voltage power systems. Would you like me to continue into the microscopic view? Of course, let's make this practical and keep it friendly and spoken in tone, with every number written out in words rather than digits. Example 1. Finding the current pulse. Suppose you have a simple circuit with a battery providing 12 volts and a resistor of 6 ohms. You want to know how much current will flow through the resistor. According to Ohm's law, current equals voltage divided by resistance. So, 12 volts divided by 6 ohms gives a current of 2 amperes. That means if you connect a 12-volt battery across a 6-ohm resistor, 2 amperes of current will flow. Example 2. Finding the voltage. Now imagine a small electric heater that draws 3 amperes of current when its resistance is 10 ohms. To find the voltage needed to produce that current, multiply current by resistance. 3 amperes times 10 ohms equals 30 volts. So the heater must be connected to a 30-volt supply to have 3 amperes of current flowing through it. Example 3. Finding the resistance. Let's say a lamp operates from a 9-volt battery and draws 3 amperes of current. You can find the lamp's resistance by dividing voltage by current. 9 volts divided by 3 amperes equals 3 ohms. So the lamp's filament has a resistance of 3 ohms when it's glowing normally. Example 4. Checking power. You can also use Ohm's law to calculate power. Take a circuit with 5 amperes of current flowing through a resistor of 4 ohms. The voltage across it is 5 amperes times 4 ohms, which equals 20 volts. Power equals voltage multiplied by current, 20 volts times 5 amperes, giving 100 watts of power being converted into heat in the resistor. 5. Changing the resistance apps. If the resistance in that same circuit were doubled to 8 ohms, but the voltage stayed at 20 volts, the current would now be 20 volts divided by 8 ohms, which equals 2.5 amperes. Notice how doubling the resistance cut the current in half. That's the inverse relationship that Ohm's law describes so clearly. These simple examples show how voltage, current, and resistance always balance one another. Increase voltage and the current rises. Increase resistance and the current falls. And the power follows along exactly as the law predicts. Would you like me to give a few real-life analogies next, like comparing electrical current to water flow, or explaining how these numbers translate to everyday devices such as lamps or phone chargers? Excellent! This is where Ohm's law really comes alive, because it connects the abstract numbers to the things we actually use every day. Let's go through it slowly and vividly, still keeping every number written out in words so it sounds natural when spoken. 1. A small flashlight bulb. Take a simple flashlight that uses a 3-volt battery and draws about half an ampere of current. According to Ohm's law, its resistance is the voltage divided by the current. 3 volts divided by 1/2 ampere equals 6 ohms. That means the filament in that tiny bulb has about 6 ohms of resistance when it's glowing. The power it consumes is voltage times current. 3 volts times 1/2 ampere equals 1.5 watts. That's roughly the heat and light you'd expect from a small pocket flashlight. 2. A car headlamp. Now imagine a car headlamp running from a 12-volt battery. A typical headlamp might draw around 5 amperes of current. If we divide 12 volts by 5 amperes, we get a resistance of about 2.4 ohms. The power is 12 volts times 5 amperes, which equals 60 watts, just about the rating printed on many automotive bulbs. So you can see how those familiar ratings come directly from Ohm's law. 3. A small phone charger. A modern phone charger converts the high alternating voltage from the wall down to a steady direct voltage of about 5 volts, and it can supply up to around 2 amperes of current. That means its output resistance, in the sense of how stiff its voltage source is very low, roughly 2.5 ohms divided by 1,000, or a few milliamps. If you plug in your phone and it draws 1 ampere, then the power delivered is 5 volts times 1 ampere, which is 5 watts. If your phone draws the full 2 amperes, it's receiving 10 watts. Those are exactly the power levels you see on typical USB chargers. 4. A laptop power supply. A laptop charger might output 19 volts at up to 3 amperes. Multiply those together, and you get about 57 watts of power, which matches what's usually printed on its label. Inside, the circuitry still obeys Ohm's law. The voltage, current, and resistance of its components all follow that same simple rule, even though the charger itself contains more complex switching electronics. 5. An electric car example. For a much larger scale, consider an electric car battery that delivers about 400 volts to the motor inverter. If the motor draws 100 amperes while cruising, the total power is 400 volts times 100 amperes, which is 40,000 watts, or 40 kilowatts. That's the kind of power needed to move a small car at highway speed. And again, it comes straight from the relationship among voltage, current, and resistance. 6. The key insight. Every electrical device, from a flashlight bulb to a smartphone charger to a car motor, follows the same law. Ohm's law is the invisible thread connecting all of them. It explains why a phone charger that supplies only 5 volts is safe to touch, while a car battery at 12 volts can light big lamps, and why high-voltage systems in vehicles or industry can move huge amounts of power with only moderate current. Would you like me to continue into how Ohm's law interacts with power efficiency?
We will move on shortly, but now let's take a break. It's been pretty heavy material. While you are recharging for the next section, I want to take a moment to share some fantastic news about an algebra course. Feel free to sit back, relax, and enjoy this fun little conversation that's going to follow. I recommend to stay tuned because there's going to be something extra about Ohm's law there as well, but in a kind of an easy way.
Welcome back to the deep dive. Today we're doing a really quick look at what you actually need to know academically for like serious work in electrical engineering, electronics, and physics research.
Right.
We're tracing this staircase of knowledge, starting with something familiar, Ohm's law,
Yeah.
VIR, and finding out what's holding the whole thing up.
Yeah, VIR is definitely where many people start. It's, perfect for basic circuits, lumped elements.
Simple stuff.
Simple stuff. But if you're aiming higher for complex research, sophisticated design, that equation, VIR, it's really just the welcome mat.
Okay, and that's where, based on the research we dug into, it gets interesting fast.
Yeah.
Because VIR, well, it doesn't stay simple.
Not at all.
If you want to deal with the real materials, fields changing over space, you
Yeah.
have to jump pretty quickly to the differential form of Ohm's law.
Exactly. And that's a big shift. You're suddenly not just looking at voltage across a whole wire. You're
Right.
looking at current density, electric field intensity,
Oh.
point by point in 3D space. And working with fields in 3D, you immediately run into Maxwell's equations. Can't avoid them. They're the fundamental rules for all electromagnetism.
Wait, hang on. From VIR, like basic circuit stuff, we're suddenly talking about the rules for the entire electromagnetic universe.
Yeah.
That feels like a massive jump.
It is, but it's totally necessary for anything advanced.
Yeah.
And that jump tells you exactly what you need to know beforehand.
Okay.
Because to even properly read Maxwell's equations, let alone use them, you absolutely have to understand vector calculus.
Vector calculus.
Right.
That's how you handle things with direction and magnitude in space, like fields.
Precisely. So Maxwell needs vector calculus. And vector calculus, well, that clearly needs basic calculus first. You can't do the fancy vector stuff without derivatives and integrals.
So we've gone from advanced EM theory back through Maxwell.
Yeah.
Back through vector calculus, down to basic calculus. We're almost at the ground floor now. What's the actual bedrock? What's supporting all of this?
And this is, I think, the most surprising bit from the source material, the ultimate foundation. It isn't some super complex math concept.
No.
It's an absolutely solid, like truly unshakable grasp of plain old school algebra.
That's it. High school algebra.
Right.
That's the secret the research points to. All that incredibly advanced engineering, the physics, it's built on algebra.
Provided you really know it.
Okay.
That's the key distinction.
Right. Yeah. We need to be clear. This isn't just, solving x plus 2 equals 5.
Not at all.
It's about being able to confidently manipulate complex, multivariable equations accurately, maybe under pressure, without making small mistakes. Is that it?
That's exactly it. The research really hammers this home. Algebraic manipulation is essentially the working language of calculus and vector analysis.
Ah, okay.
So if you're shaky on the algebra, even slightly, it creates this hidden bottleneck. You might think you're struggling with, say, a vector calculus concept in Maxwell's.
Yeah.
But the real problem is actually an algebraic slip-up you made a few steps earlier, and maybe you don't even realize it.
Wow. So if that foundation's weak, everything built on top is unstable, you basically have to fix the algebra first.
That's what the analysis suggests. Before tackling the advanced stuff, you need to ensure that algebra is absolutely rock solid. It's about readiness.
And the sources mentioned a specific way to address this.
They did. They highlighted the need for a dedicated approach. One example mentioned was a video series and member area. I think it was called Algebra Prime.
Algebra Prime, right?
Designed specifically to build that core algebra skill from the ground up, making sure you're truly ready for calculus and beyond. So you're not fighting with the basics when you need to focus on the complex ideas.
So the takeaway here seems pretty clear. If you're serious about this stuff, you now know where the most crucial leverage point is for your study time.
Yeah, prioritize that foundation.
It's kind of ironic, isn't it? The most basic thing is actually the most critical.
It really is. And, that brings up a final thought, something for you, the listener, to consider. Since all this high-level physics, this complex engineering, ultimately rests on mastery of basic algebra. Well, How often do really smart, highly trained experts get stuck on incredibly difficult theoretical problems? Only because, deep down, they're actually wrestling with an old, maybe unrecognized algebraic weakness, a vulnerability from maybe 10th grade that never got fully fixed.
That's
If,
actually a pretty unsettling thought, something definitely worth pondering.
Yeah.
Excellent. Let's touch on that briefly and clearly, because output resistance, sometimes called source resistance, is a subtle but very useful concept when thinking about real-world power supplies. When we talk about output resistance, we mean how much a power source's voltage drops when you draw current from it. A perfect voltage source would hold its output voltage absolutely steady, no matter how much current you take. Its output resistance would be zero. But in the real world, every source has a little internal resistance. When current flows, some of the voltage is lost across that resistance, causing the output voltage to sag slightly. For example, if a small 5-volt phone charger has an effective output resistance of only a few thousandths of an ohm, drawing 1 ampere of current might cause the voltage to fall by only a few millivolts, barely noticeable. But if the internal resistance were higher, say half an ohm, then 1 ampere of load current would drop the output by half a volt, leaving only 4.5 volts available to the phone. That's why a low output resistance is a mark of a strong, well-regulated power supply. It can deliver current without its voltage collapsing. You can think of the charger as a 5-volt battery with a very tiny resistor inside it. The smaller that internal resistor, the stiffer the supply, meaning it can hold its voltage even under heavy load. Electronic designers often model any source as an ideal voltage source in series with a small internal resistance, because that simple picture lets them predict how much the voltage will droop when current increases. In summary, output resistance describes how much the source's voltage changes when current changes. Lower output resistance means better voltage regulation, steadier performance, and happier devices connected to it. Excellent. Let's focus now on Ohm's law in AC circuits with purely resistive loads and keep everything clear, practical, and intuitive. No unnecessary math complexity, just how things really behave when the voltage and current are simple sine waves. The starting point, what purely resistive means. A purely resistive load is one that behaves exactly the same way on alternating current as it would on direct current. It turns electrical energy straight into heat or light without storing any of it in magnetic or electric fields. Examples include the filament in an incandescent lamp, an electric heater, or a resistor used for testing or current limiting. These are called ohmic devices because they obey Ohm's law perfectly. Open quote, voltage equals current multiplied by resistance, close quote. 2. The voltage and current waveforms in an AC circuit, the supply voltage is sinusoidal, meaning it varies smoothly like a sine wave, rising from 0 to a positive peak, back to 0, then to a negative peak, and so on. When that sinusoidal voltage is applied across a purely resistive load, the current follows exactly the same shape and timing. It too is a sine wave, rising and falling perfectly in step with the voltage. This is an important point. Open quote. In a purely resistive circuit, voltage and current are in phase. They reach their maximum, cross 0, and reach their negative maximum at the same instance of time. Close quote. There's no delay between them. They move together like two dancers perfectly in sync. 3. Ohm's law still holds instant by instant. Even though the voltage and current are constantly changing, Ohm's law is still true at every moment. At any instant of time, open quote, the instantaneous voltage equals the instantaneous current multiplied by the resistance, close quote. If you were to take snapshots of the wave at 1,000 different points during the cycle, that relationship would hold every single time. 4. RMS values, how we handle the math in practice. Because AC voltage and current keep changing, engineers use a special way of expressing their effective values, the RMS value, which stands for root mean square. The RMS value of a sinusoidal voltage or current is the steady DC value that would produce the same heating effect in a resistor. For a sine wave, the RMS value equals about 0.77 times its peak value. So if you have an alternating voltage that peaks at 141 volts, its RMS value is 100 volts. That's why ordinary mains power in many countries is said to be 100 or 220 volts. Those are RMS values, not peak voltages. 5. Using Ohm's law with RMS values. When working with sinusoidal AC and purely resistive loads, you can apply Ohm's law exactly as you would in DC, but use the RMS values of voltage and current. Open quote. RMS voltage equals RMS current multiplied by resistance. Close quote. This makes all calculations straightforward. If you know the supply voltage and the resistance, you can find the current. If you know the current and resistance, you can find the voltage. And you can find power by multiplying voltage and current, because for a resistive load, they're in phase. 6. Example in words. Imagine an electric heater connected to a 120-volt AC supply, RMS voltage. If its resistance is 60 ohms, the current is the voltage divided by the resistance, 2 amperes. The power converted into heat is voltage times current, 240 watts. Everything works exactly like DC because there's no phase shift and no reactive effects. Only the instantaneous values oscillate up and down. The average power over time stays constant. 7. Power in a resistive AC circuit. Because voltage and current rise and fall together, the power, which is their product, is always positive. When voltage is positive, current is positive. When voltage is negative, current is negative. In both cases, their product is positive. That means energy is always flowing from the source into the resistor, never back. The resistor simply turns it into heat continuously, even though the voltage and current themselves reverse direction. 8. The essence. So for a purely resistive AC circuit, voltage and current are perfect sine waves that stay in phase. Ohm's law applies at every instant, just like in DC. For practical work, we use RMS values for voltage and current, so the formulas look identical to those in DC analysis. All the power drawn is real power. No energy is stored or returned to the source. That's a very sharp and important observation, and you're absolutely right to notice the subtle direction implied in the wording. Let's unpack it carefully, because this touches both the physical causality in circuits and the mathematical form of Ohm's law. 1. The law itself is symmetric, not causal. Mathematically, Ohm's law simulates a proportional relationship between 3 quantities. Open quote, voltage equals current multiplied by resistance. Close quote. That relationship itself doesn't imply which one causes the other. It just says they're linked by that constant factor. You can rearrange it in any direction you like. Voltage equals current times resistance. Current equals voltage divided by resistance. Resistance equals voltage divided by current. All are equally correct statements of the same law. 2. In physical practice, voltage is usually the cause mountain. In real-world circuits, you're absolutely right. We usually apply a voltage, for example, connect a resistor to a battery or power supply, and then the current results from that voltage and the resistor's value. So, physically speaking, the voltage source drives the circuit, and the current is the consequence. That's why, when teaching or analyzing circuits in a practical sense, it's often more natural to express the law as, open quote, current equals voltage divided by resistance. Close quote. This form aligns with how you'd actually measure or predict behavior. You know the supply voltage and the resistor's value, and you calculate how much current will flow. Haja 3. Why textbooks sometimes write voltage equals current times resistance? Historically, Ohm's experiments were done by measuring how the potential difference across a conductor changed as he varied the current through it. He was observing the relationship, not necessarily driving one quantity or another. So the original mathematical statement was simply a correlation. The voltage across a conductor is proportional to the current through it. That's why in pure theory, the expression is often written as open quote, voltage equals current multiplied by resistance, close quote, without assuming which one causes the other. It's the simplest way to show that voltage rises in direct proportion to current for a given resistance. 4. The direction of cause and effect depends on the situation. In a voltage-driven circuit, like connecting a resistor to a battery, voltage is the cause, current is the effect. In a current-driven circuit, like a current source driving a resistor, current is the cause, voltage is the effect. So both forms can be right. It depends on which quantity you treat as the independent variable in your analysis. 5. The deeper point, Ohm's law is descriptive, not prescriptive. Ohm's law itself doesn't say how voltage or current come to be what they are. It only states how they are related once the circuit settles. The actual cause is determined by what kind of source is providing energy to the circuit. That's why physicists and engineers treat it as a constitutive law of the material. The voltage across a conductor and the current through it always satisfy that ratio, no matter which one you decide to control. Answer 6. In short, mathematically, Ohm's law is symmetrical. It doesn't imply direction of cause. Physically, in most practical circuits, voltage is what's applied and current follows. So in everyday reasoning, it's clearest to think, open quote, the voltage is given, the resistance is known, therefore the current is derived, close quote. Excellent. That's a truly insightful and practical question. You're noticing that in everyday electronics, we nearly always deal with voltage sources, batteries, power supplies, AC mains. So the idea of driving with current can feel abstract or even backwards. Let's reason it through step by step and connect it to real circuits. What a current source really means. A current source is a device or circuit that tries to maintain a specified current, regardless of what voltage is required to make that current flow through the load. That is the opposite of a voltage source, which maintains a specified voltage and lets the current vary as needed. So, in a current source, you set the current, the cause. The voltage across the load adjusts automatically, the effect, to satisfy Ohm's law. Mathematically, for a resistor, open quote, voltage equals current times resistance. Close quote, if the source keeps the current fixed and the resistance changes, the voltage changes accordingly. 2. A simple real-world example, constant current power supply. Imagine a battery charger for an LED or a laser diode. These devices are very sensitive. A small change in current can drastically change their brightness or even destroy them. So instead of applying a fixed voltage, we use a constant current driver that forces, say, 500 milliamperes through the LED. The driver adjusts its internal voltage automatically to whatever value is needed to make that current flow through the diode. If the LED warms up and its resistance drops, the driver lowers its voltage to keep the current steady. If you add another LED in series, the driver raises its voltage so that the same current still flows. That's a perfect example of a current-driven circuit. The current is fixed by design, and the voltage is the result. Number 3. Another simple way, resistor plus op-amp current source. You can build a practical current source with a voltage reference, an operational amplifier, and a resistor. Here's the basic idea. The op-amp measures the voltage across the resistor and adjusts its output so that a specific current flows through the load. The resistor sets the current. If you put 1 volt across a 1 kilo ohm resistor, the current is 1 milliampere. The op-amp raises or lowers its output voltage automatically to maintain that current through the load, whatever the load's resistance happens to be. This is how precision current sources or active loads are built in laboratories. 4. Electronic current sources are everywhere in disguise. Even if you rarely see a box labeled current source, the concept appears in many everyday circuits. Transistor bias circuits. The collector or drain current is set almost constant by resistors and emitter or source feedback. LED drivers keep light output stable by holding current constant, not voltage. Battery charging circuits limit current during charging to protect the battery. Current mirrors. In analog ICs, these distribute precise currents independent of voltage. Each of these is a practical way the world implements current causes, voltage results. 5. Physical analogy. Think of a pump that delivers a fixed flow rate of water, regardless of what pressure it must build up to push that flow through the pipe. If the pipe is narrow, the pump's pressure rises. If the pipe is wide, the pressure falls, but the flow stays the same. That's exactly how a current source behaves electrically. Voltage corresponds to pressure, and current corresponds to flow. 6. How you'd set it up in a lab. If you wanted to see it yourself, you could. Take a bench power supply that has both voltage and current control knobs. Set it to current limit mode, say to 1 ampere. Connect a variable resistor, a rheostat, across it. As you change the resistor value, watch what happens. the supply automatically adjusts its output voltage up and down to keep the current exactly at 1 ampere. That's your real-world hands-on demonstration of a current-driven situation. 7. The key difference in viewpoint. Voltage source. Voltage is fixed. Current depends on the load. Current source. Current is fixed. Voltage depends on the load. Neither is more correct. They are two complementary ways of defining what the source controls. But because real physical voltage sources are easier to build, most circuits are voltage-driven, while current sources are used in special cases where precise current control is essential. 8. In short, you can absolutely have current causes voltage effects in real life. It's not just a theoretical curiosity. It's how LED drivers, transistor bias networks, and lab power supplies often operate. All you need is a source that actively adjusts its voltage to keep the current constant.
We will move on to the next section shortly, but before that I want to share something that might be very useful for you. Inspired by successful YouTube creators making fortunes from their channels, then Tube Mastery and Monetization course from Matt Park can help you get real results on YouTube with personal attention from him and his content team. Lots of people have already succeeded with their channels thanks to him. He also has Tube Magic software tool that can help you accomplish more when it comes to making content. Links in the description. I've also prepared a video for you that talks more about that, as well as solutions to challenges like online security, financial progress, and additional creativity. There, we'll explore these topics with respect and care for you. I warmly invite you to watch this video when you get a chance. Either way, your support is the current that powers this channel. And now back to the show.
Excellent. That's exactly the right next step. Now that you've seen how current and voltage sources work in practice, let's step back and look at how circuit theory defines and uses them as idealized elements that let us analyze and predict circuit behavior in a clean mathematical way. Number 1. The role of sources in circuit theory. Every circuit must have at least one source of energy, something that pushes charges through components. Circuit theory describes these sources in two fundamental complementary forms. The voltage source, which maintains a specified voltage difference between its terminals, and the current source, which maintains a specified current through its terminals. These are ideal building blocks, simplified models of real-world devices. They let us analyze even complicated networks using systematic methods like Kirchhoff's laws, Thévenin's and Norton's theorems, or superposition. 2. The ideal voltage source. An ideal voltage source is defined as a two-terminal element that maintains a fixed voltage across its terminals, regardless of the current flowing through it. The voltage is constant, or follows a given function of time. The current can be anything, positive, negative, or zero, as required by the rest of the circuit. In other words, it can source or absorb any amount of current necessary to hold its voltage. Mathematically, you can think of it as having zero internal resistance. That means if you short-circuit an ideal voltage source, infinite current would flow, which is, of course, impossible physically, but perfectly fine for theoretical analysis. Real-world approximations. A battery, power supply, or regulated converter behaves approximately like a voltage source. It keeps its voltage roughly constant as load current changes, at least within some limit. The small deviation, the voltage droop when current increases, is modeled by a series internal resistance in circuit theory. So, in analysis, we often treat a real source as an ideal voltage source in series with a resistor, that resistor representing the source's internal impedance. 3. The ideal current source. An ideal current source is the dual of the voltage source. It maintains a fixed current through its terminals, regardless of the voltage across them. The current is constant, or follows a specified waveform. The voltage can be anything necessary to sustain that current through the external circuit. Mathematically, it has infinite internal resistance, meaning it never allows current to leak elsewhere. If you open circuit an ideal current source, it would have to produce infinite voltage to keep current flowing. Again, not physically possible, but valid as a model. Hashed real-world approximations. Transistor circuits, LED drivers, and lab current sources behave approximately like current sources over some range. To represent a real current source, circuit theory adds a parallel resistance, finite internal resistance, to the ideal current source. This accounts for the fact that its current slightly changes with load voltage. Number 4. Duality between the two voltage sources and current sources are dual to each other. They are two sides of the same conceptual coin. Because of this duality, many circuit theorems come in pairs. For instance, Thévenin's theorem, voltage source form, and Norton's theorem, current source form. 5. Using sources in circuit analysis. In circuit theory, we use these sources as starting points in network equations. For example, a voltage source sets the voltage difference between two nodes. A current source sets the current entering or leaving a node. Once those quantities are fixed, we can apply Kirchhoff's laws. Kirchhoff's voltage law, KVL, the sum of all voltages around a loop is 0. Kirchhoff's current law, KCL, the sum of all currents entering a node equals the sum leaving it. These let you solve for unknown currents and voltages throughout the circuit. Number 6. In analysis versus in reality. In theory, voltage and current sources are perfect and can supply or absorb infinite power. In practice, every real source has limits: maximum current, voltage, and power dissipation. We model those limits by adding internal resistance or by specifying maximum ratings. But ideal sources remain essential in analysis because they make the equations elegant in general. After solving the idealized problem, you can then adjust for non-idealities if needed. Number 7. In summary, voltage sources fix the voltage. Current sources fix the current. They are idealized, complementary elements that make circuit theory work. Real devices approximate these ideals over limited ranges. The relationship between them is beautifully symmetrical, allowing easy conversion between Thévenin and Norton forms. In analysis, they provide the driving conditions for a network. What forces it to have current and voltage everywhere else? Would you like me to continue next with Thévenin's and Norton's theorems? All right, let's talk about differential resistance in a way that's very intuitive and smooth for reading aloud. Imagine you are looking at a transistor's characteristic curve on a chart. You see the voltage on the horizontal axis and the current on the vertical axis. In many basic cases, we talk about the instantaneous resistance by just dividing the voltage by the current at a single point. That gives a rough idea of how much the device resists the flow of current to CO, but it can be misleading if the curve is not a straight line. Now, differential resistance is a bit more subtle. Instead of taking the total voltage and total current, you look at a tiny change in voltage and the corresponding tiny change in current around a specific operating point. Essentially, you zoom in on the curve and ask, if I nudge the voltage just a little, how much does the current respond? This gives a local slope of the curve. When the slope is steep, a small voltage change causes a large current change, so the differential resistance is low. When the slope is shallow, the current barely changes, even if the voltage moves a little, so the differential resistance is high. This approach is particularly important for transistors and other nonlinear devices because their curves are rarely straight. By using differential resistance, you can understand the dynamic behavior at a particular operating point, which is crucial for designing amplifiers or understanding small signal behavior. In short, think of differential resistance as how the current responds to a very small nudge in voltage, rather than the average resistance over the entire voltage range. It's a snapshot of the slope at one point on the curve, capturing the subtle local behavior that ordinary resistance might miss. If you want, I can make a visual analogy using a gently sloped hill to make the concept even more intuitive for TTS.
Thanks for watching to the end of this video. If you want more content like this, there is a playlist that should be popping up right now. Stay tuned for more. I've also made this free video for you with solutions for creativity, financial strength, and online security. I hope you'll enjoy this offer as well as all the others featured on my channel. And that concludes this video. Thanks for watching, and until next time, this is Hermalau Tube. My name is Konstantin, reminding you that your interest is the current that powers this channel.